Tiago, whenever you want to start. Sorry for the delay.
Sure. Can anyone see my screen?
Yes.
Okay, good. So, as José said, I'm here today to present this work that we have been doing during the Embers project, entitled as the Market Integration Analysis of Heat Recovery under the Embers platform, and the case study applied on an industrial park in Greece. So I will start with a brief introduction on the subject, then present in a general way the Embers platform, and I will talk briefly about the market module of the Embers platform and the case study from Greece that we have been used to test and validate this model. The main results and conclusion will be also presented. So, the continuous development of heat recovery technologies, for instance, through heat pumps, has been allowing industry to recover waste heat from processes that were previously difficult or inefficient to perform. For instance, supermarkets can now efficiently recover waste heat from the freezing systems, and therefore this recovered heat can be used for other process or even be injected in the district heating network if available. So industries and small-scale buildings are no longer only consumers, but can also be producers and therefore become prosumers. So this enables the ability to buy and sell surplus heat from other agents in the system. For this to be possible, the access to district heating networks needs to be, of course, liberalized in such a way that allow these new prosumers to buy heat and when they need, and sell surplus heat from their recovery system when available. With this ability, prosumers may be able to participate in the district heating market and increase their revenue or reduce their own consumption costs. However, new or updated marketplace are required to allow this trading system for heat and cold. So, under this motivation, the Embers platform has been developed to allow different users to access the potential of waste heat recovery in the district heating networks. More precisely, the Embers platform consists of 5 distinct models. Okay? The first one is the core functionalities model that collects all the data required for the simulations and transform it according to the needs of the remaining models. Then we have the GIS model. This is the Geographic Information System model that allows to setting the path between source and sinks. It can complement the path for adding new source in the district heating network or even simulate a completely new one. Then we have the TEO model, so the Technical Economic Optimization module, that performs an in-depth analysis and dispatch of all source, taking into account the sink needs. It sets all source needed for supplying the expected sinks. And after this, we have the market model that will be the focus of this presentation. And in general, this model allows source and sinks and prosumers to assess their behavior in a competitive and liberalized market platform, considering the traditional and innovative market clearing process. Finally, we have the business model that allows evaluating the different business options, getting high-level information for the recovery of the investments and so on. So, focusing on the market module, we have built this model to consider the traditional, this is the centralized mechanism, market clearing, and also some decentralized innovative market clearing process. So first one is the common model used in the electricity markets and also in the heating markets. So using the uniform pricing scheme. And then we implemented also a decentralized one based on the peer-to-peer exchange, which allow the things to choose what source they want to buy energy from. In addition, we implemented also the product differentiation mechanism in this decentralized market, which allows the user, okay, so the things to choose based on some differentiation to what source they want to buy the energy. For instance, if we use the preference of CO2 emissions, we are saying that the things have preference to buy energy, so buy the heating and cold from the source that does not cause so many CO2 emissions in the system. So for this, we use this product differentiation mechanism that is based on a penalty scheme that penalizes or benefit. Okay, it can be a penalization or a benefit, depending on the things perspective. So the market model is composed of two different analyses. One is the short-term analysis, where we have to choose what kind of market design we will assume for simulations. We have to, of course, define some bids regarding the source and things, so the energy and price that the source are willing to offer, and the same for the things. And then with the short-term analysis, we can get so the energy dispatch, market clearing price, the settlement for all the agents in the system, the social welfare of the market, and other indicators that can be given by this model. In addition, we have also the long-term analysis that comprise, as the name indicates, a market analysis and participation of the source and sinks in the market in the long term. So this gives, of course, the energy dispatch, but it also gives other key performance indicators that can be useful for the source and sinks assess their revenue and participation in the market. For this specific case, and here today, we have used the long-term analysis. So, as a case study, this works, of course, used an industrial park located in the northern Greece. This industrial park comprises both small size and high size energy industrial companies with different seasonal profiles and requirements. This case study comprises 4 sources and 6 sinks. Each one of these have also different streams with different needs and fluids. the supply temperatures, target temperatures, and so on. Most of these agents are located within the Volos industrial park in Greece. And in addition, the grid is also considered to cover the heat demand in case of the heat shortage from the industries. The collected data from the Greece case study was sent to the models, and after several iterations of the market model, it receives all required data to run a full year simulation with daily resolution. Okay? So more precisely, each agent in the market defines its bids, energy, and monetary, of course, and also CO2 signals and the geographic data. So to show the market model effectiveness on the long-term simulation, we have some results where, for instance, this graph shows the successful participation in the market, okay, which assess if one agent is participating in the market or not for each time frame. Here we have in average. So we can see that the agents, we have these 4 agents plus the grid, so are the source, and we can see using the decentralized mechanism and also the product differentiation, what is the percentage, the average percentage of participation of these agents, this source in the market, how much they, how many times they are scheduled in time. Also, we have other graphs representing the average dispatched generation, which indicates how much from the available energy is scheduled. In this case, the higher emissions from Aliborgia are in focus because the share of the dispatched heat decreased to give place to other agents with less CO2 emissions. And then we have also the general results about the energy that have been dispatched throughout the year, and also the settlement for each of the source, and considering the different market mechanism. Here we are comparing the decentralized and the decentralized with the product differentiation regarding the CO2 emissions. Here we can see that the MPEG sink is not participating in the market in any period, so is not dispatched. This happens because this sink is offering the lowest bid to buy heat, so pushing it to the last position in the merit order curve is, if we are talking decentralized mechanism. But in the centralized, no one will, no source will want to provide a sink that is offering lower than their marginal operating costs. So this means that in certain periods, this agent will not find an available match for providing the heat. In what concerns to the net balance, there are some difference in the dispatched amount, which is related to the market adjustment to the penalties. Of course, the settlement presents revenue for all agents, taking into account the revenue according to the energy perceived price in the market. We should mention that all agents present the same settlement values for both market designs, except the manuals. This is supported by the product differentiation, okay, that only taking effect on Sundays for most agents. And in this particular day of the week, the market clearing price is zero. So to summarize, we have been proving that the Embrace platform it's working and all the models are being effectively and work as we expected, not only in some offline simulations, but also in online simulations, as this one presented here. This platform also allow all the users to access to assess these investments in terms of the return that they will get from participating in the different markets. I'm talking especially about the market model framework. And of course, these new designs that we present, these new market designs we present in this platform allows not only end users but also government institutions to assess and simulate the impact that these kind of systems and, for instance, communities and so on, energy communities, the impact they can have in the system, in district heating systems and so on, and therefore in the environment and of course in the economy around these systems. So, do you have any questions?
So now we open the panel to the attendants. If anyone has a specific question to Tiago. Tiago, I have a general question. So, in your view, what are the main advantages of a decentralized market versus a centralized solution for district heating networks?
Okay. Well, the decentralized market allow us, or these new innovative market designs allow consumers, or in this case, sinks, to establish a preference, so they can choose who they want to buy energy from, and not only just buy the energy from the operator or the commercializer without knowing if this energy they are consuming is from what kind of source. So in this end, these market designs can enable the things to directly negotiate the energy they want to buy or sell in the case of source or prosumers to source and prosumers they prefer. So this is not possible in the current market frameworks. And this is why we believe this is an advantage for the district heating networks. These markets can be innovative in this way, and of course allows or brings more freedom of choice, and also can encourage and enable energy communities in these systems. Because if we may have in the future energy communities regarding also district heating networks, these communities can have preference to choose who they want to buy or sell energy from and to. So this is the main innovative goal, I would say, of these innovative markets to be applied in district heating networks.
Thank you for the answer. Another question that just I think it will be good to know is, in your view, well, district heating networks are inherently local infrastructure and require huge sums of investment, and they, well, it's not easy, technically feasible to extend them for more than a couple of 100 miles. So, in your view, what are the main impediments of the widespread of these type of solutions?
Okay, so there are, of course, some barriers that we, technical barriers and other kind of barriers that we can take into account when applying these kind of markets and so on. But even even through the district heating network is more localized or located, more restricted in terms of the number of agents and so on we will have in the system. We we can see that there are many consumers, for instance, in the northern countries, that have the willing to choose who they want to buy energy from, and some of them, of course, also are also willing to participate in some investments in their community to increase their self-sufficiency on providing heating and so on. So these markets will allow these consumers and prosumers that are willing to to invest in the system, regardless the traditional, very increasingly expanding of the network. Of course, the network is needed and is already there. So why the question is why we cannot also take advantage of the existing district heating networks and select who we want to buy or sell energy from, and this is more even more innovative nowadays with the the developments and continuous developments in the technologies, for instance, the heat pumps in the supermarket. So as they become prosumers, they want to sell energy. If they go to the traditional district heating network system, if they don't update, they face many barriers to sell their excess heat. So these are new ways that can enable or allow, or I will say facilitate the trading of this waste heat energy that is becoming being available from many different sources in the current district heating networks.
All right, Tiago, thank you very much for your presentation. In the
Thank
end
you, Jose.
of all the presentations, we'll have a brief panel opening. So if anyone wants to ask further questions, they will be willing to do so. Now I want to present the next speaker. Is Shravan Kumar Pinayur Kanan. He's a PhD student at the Division of Energy Systems in KTH, and his research is focused on the decarbonization of industries through recovery, recycling, and reuse of energy within industries. The research encompasses the development of a tool for long-term energy investment planning in industries. And his presentation is titled, I'm sorry, just give me 1 second. The next techno-economic and spatial analysis of integrating excess heat in the Swedish district heating system. Shravan, the panel is yours. Thank you.
Thanks, Joseph. I'll just share my screen, make sure everything's working fine here. I hope it's the right screen. It's being shared. Um, yeah, thanks. So, hi everyone. Like Jose said, I'm Shravan. I work at the Division of Energy Systems at KDH. I'm a PhD candidate, and my focus is on district heating and decarbonization of industry and sector coupling between district heating and industry through excess heat recovery. Um, this presentation is about the techno-economic and spatial analysis of excess heat integration into a Swedish district heating system. Yeah, it's part of the project that me, Jagrati Thakur, and Francesco Gardamino, my supervisors, have been working on together. So, general outline of this presentation, we'll go through first the background and the purpose and aim of this work, a little bit on the research questions, and the methods and the results. The word initial conclusions might be an oxymoron, but it's initial conclusions because there's a lot more of this study that comes in the future work. So that's why I have it as initial conclusions here. So a little bit of the background on excess heat recovery and in the context of Sweden. So we have about 9 terawatt hours of excess heat, which is rejected annually from different types of sources. Might be high temperature excess heat in industries, slightly low quality excess heat from data centers, and urban excess heat sources. And Heat Roadmap Europe, which was a previous study and a project which looked at connections and overlaps between available excess heat sources and existing district heating networks. And it assesses a ratio of assesses the excess heat ratio, which is basically the ratio of excess heat available against which is overlapping with the district heating networks, and the ratio of this against the heating demand in these buildings which are connected to these networks. And based on the results from this project, we saw Sweden has a excess heat value of rather than 1, which means that there's more excess heat available in the overlapping sources than there is demand for the buildings that are connected to these district heating networks which the sources overlap with. So this was then further used in a study by Mans et al., where they mapped different types of excess heat sources from flue gas cooling in Sweden. And that's what we see in the figure on the right, where we see large excess heat sources from different types of industries that are located across the country, especially large sources in regions such as Gothenburg, where there are 2 or 3 large sources of refineries. And there's a large iron and steel plant which is very close to the excess heat system of Oxelösund, which we'll now see in the coming slides how these sources have been used. But there are also a cluster of very small sources that are located in the Stockholm region, which forms the main case study analysis for this particular presentation. So moving on to a general context of district heating in Sweden. District heating has been a rather popular source of heat supply in most urban centers and also in smaller towns. The market share of district heating has gone up since 1960, and it's been accelerated after 1970 with the oil crisis. And of late, it has still been a sustainable business model, especially due to green certificates that are provided to combined heat and power plants, which run mostly on biomass and waste heat. So a lot of heat coming in these district heating systems is also renewable heat. So here we see the fuel share of heating in general, not just district heating, and we see how district heating dominates most of the heat supply, eliminating almost all oil. And the rest of the heating usually comes out of 3 sources, and those are usually in houses that are in countryside, which are not connected to the district heating system, and they use either electric boilers or natural gas boilers or biomass based boilers too, and also some heat pump for the heating purposes. But then the fuel share within the district heating system itself is largely renewable, depending on how one looks at biomass and biofuels. But it's mostly dominated by biofuels and waste incineration right now. There's not just local waste incineration, but waste is also imported from abroad into the district heating system for incineration and providing heat. There's a small share of, or rather significant, but not that significant share of flue gas condensation and industrial excess heat right now. in the district heating system. It adds up to about 20%, but flue gas condensation also includes some CHP plants. So it's not entirely excess heat, and it again depends on the way one looks at it. And there's very small shares of course, heat pumps, natural gas, and some fossil and peat. So there have already been sources of excess heat in the Swedish district heating system, like we saw in the in slide 3, with the mapping of the large sources. So, like we saw in Gothenburg, it is the largest source or user of excess heat in the district heating system by energy terms, with about 30% share of district heat. But most of them come directly from oil refineries. Although excess heat from oil refineries is considered to be a clean source of heat in the Swedish district heating system. We also have some smaller, a higher penetration of almost 100% in some smaller towns where the heating is completely reliant on industrial excess heat. And it's worth note that when district heating first started in Sweden, when it was industries that were local industries connected to the a public heating grid, so it's not a new thing to have excess heat in the Swedish district heating network. So the aim of this study is to look at the techno-economic potential of integrating local excess heat sources into an existing district heating system. And to do this, energy system models offer an excellent opportunity to analyze various investments and conduct a least cost-based optimization for the best socioeconomic case of investments in district heating and excess heat recovery. But then it's also very important, on the other hand, to consider how an existing thermal grid should be modified or extended to include these excess heat sources, especially when they are large, since that forms one of the largest parts of the cost in the investment. So the study then focuses both on the long-term development of district heating systems within Sweden, while looking at current energy policies and resource constraints and so on, but also with an objective of including the cost for extending the existing thermal grids, and having a strong computational base for calculating these costs accurately and capturing them as a part of the investment plan. So then we look at 3 questions, which we try to answer using these both the spatial analysis and the techno-economic analysis. Is what is the cost effective, or how much excess heat can actually be recovered while still being competitive with the existing technologies, and what is exactly the potential that we have right now, which is the technical potential, and how can one actually harness this potential when looking at a cost competitiveness perspective, and how to make it more cost competitive. And most importantly, from a cost optimization perspective, when and where to invest. So which excess heat sources are best, and at what point in time do they become cost competitive. So then the methodology focuses on 3 steps. The first step will be a literature of looking at what previous studies have looked at in this region regarding excess heat, and if there are any mappings of excess heat sources with respect to the district heating grid. The second step would be to collect the data of these sources and sinks with the locations of the grid in these different regions, and look at other techno-economic characteristics of the existing plants and also the excess heat sources. And also very important to consider here is the future investment plans for district heating system and how that develops, and thereby affecting how competitive excess heat is in the future. So the last step would be the modeling. There we consider 2 tools, with a geospatial tool, which will be looking at the extension of the grid and calculating the costs and the corresponding losses from that. And we also use the long-term open source energy system model, osmosis, for looking at cost competitiveness of the excess heat comparing to the existing plants by doing a long-term optimization of the district heating systems. So a little bit more on the tools itself. So yeah, like I said, we use the long-term open source energy system model, osmosis, and this model has been further modified as part of the TEO module of the Embers platform that was presented in the previous presentation. So this is it's an open source model that considers long-term investment planning for energy systems in general. It's a deterministic model that focuses on a technology commodity representation of the energy system. Um, and it's focused on a socioeconomic optimization, and the objective here is to minimize the overall cost of the system. So the Python version of osmosis in the package called pulp has been used and modified, as I said, in the embers project, and that has been used for this study. And the spatial analysis model is also from the based on the, or it is actually the GIS module of the embers platform, which looks at the spatial dimension of the network. And it consists of two mixed integer linear programming models that look at creating a least cost network, a least cost connection between excess heat source and an existing grid, and then optimizing the capacity of this network based on the exchanged heat, and thereby calculating the costs and the losses from this network. So it's based on the road network graph from OpenStreetMaps, and the calculation accounts for the investment cost, and to calculate the losses, it considers the ground and ambient temperatures that supply and return temperatures of excess heat. So the models have been soft linked with the results of the geospatial model acting as an input to osmosis. So we compute the least distance connection between the existing source and the grid, and we forward the cost and the losses of this connection to osmosis, which then adds to the capital cost of these technologies and also the losses in these technologies to then form a part of the energy system model's inputs. So the initial case study considered the case of Stockholm, where we had several small and large sources of urban excess heat. It was based on a study by Changsu et al., who mapped the sources of urban excess heat within the Stockholm municipality. And based from this study, we found out 5 types of sources with the temperatures and the annual excess heat potential from each of these sources. For this study, we considered only sources that were so we considered supply and return temperatures of 95 degrees and 60 degrees, considering a third generation district heating system. Thereby, we considered only temperatures above 40 degrees Celsius to make the system more analysis more realistic and the system more technically feasible. So we considered data centers, ice rings, and sewage plants as the sources of excess heat. And so the model was then built from 2022 to 2050 in 5-year time steps, which represents every 5th year. So 2022 and 2027 and 2030, and after that every 5th year until 2050. 288 interannual time slices are considered. So this considers all 24 hours of the day, and it's bulked up as of 12 months. So this is to obtain both a daily and a seasonal variation in the heat availability and heat demands. We modeled the existing plants along with the identified heat sources, which were bulked up based on the source type. And the techno-economic parameters was obtained from the open database that was established during the embers project. And the future investment plans, we could not obtain completely the exact investment plans of the district heating company, but then we decided to have replacement of current plants when they at the end of the lifetime with similar technologies. So based on the initial results, which were basically grouping up all of the sources as the based on the source type and getting an average network extension cost, we found that the utilized potential of the excess heat sources were far less compared to the technical potential. So the highest we could achieve was about 6% of penetration for the ice rings, which also had a good overlap with the district heating system and the lowest cost of all the source types. But this is also a direct reflection of how the clustering by source type is not a good method to follow to get these results. And also this result is also skewed to a large extent because of the application of green certificates for CHP plants, making them extremely cheap compared to excess heat investments. So the initial conclusions was that low penetration is of course because of the lower temperatures and higher investment costs for excess for heat pumps, but also they're not able to compete against CHP plants that get green certificates, which dominate most of the excess heat share. Also, there should be a balance of approach between the source type based clustering and representation analysis, the model, and the representation of the spatial clustering in the spatial model. So all the source type do not form the same spatial cluster, so that creates a problem in the inputs between the two models. And of course, we also need to consider the spatial growth of the network in the future. So for example, if a excess heat source is very far out from the grid today, it might not be the same in a few years, because there would be growth of demand and the grid would anyway extend to those parts, since it makes business sense for the grid to extend. So that is another thing that needs to be considered. So like I said, a lot of work in this study is yet to come. So we will still need to balance out between the spatial clustering on also an approach of considering each of these sources, so calculating the extension cost for each source, and then putting them as a separate technology in the model, which needs to be balanced out in terms of computational and time resources. Also, green certificates for biomass plants until 2050 needs to be thought about again, and there needs to be a resource constraint for biomass, and also to stop the sort of green certificates in CHP plants after some point of time until 2050, since it's not realistic to have them until 2050. There's also introduction of heat storage for certain clusters of large excess heat to determine if it's actually feasible for short or long-term heat storages. And in the future years, there'll also be focus on fourth and fifth generation district heating systems, thereby reducing the temperature that needs to be boosted from these low temperature excess heat sources. And that will be based on both technical feasibility and the district heating companies' plans if you manage to obtain them. So the last bit of the future work will also introduce a stage 3 in this multi-model approach, where we'll have a dispatch model at the end of the analysis. So key selected years from the long-term investment will be fed into the dispatch model to check if the capacities that are determined by the long-term investment model is technically feasible at an hourly resolution. This is mainly because there's large-scale variation in excess heat availability and also heat demands, which might not be captured in a 288 times less interannual time resolution. So we wanted to have another stage where we'll have the dispatch model check out the technical feasibility of the solutions. Thank you.
Hi, Shravan. Thank you for the presentation. You have one question from the audience. It's can you see it? It's wondering what biomass potential estimation you are using. Do you rule out consider land food conflicts when sourcing biomass?
Yeah, so that is something that I did not consider for the initial study, but that is something that we're planning to consider as a part of the extension of the study, because we do not consider any resource constraints for biomass, but it is very important that we consider that. So we're going to look at the possible penetration of biomass in different sectors, and how that will affect the biomass availability for district heating, and going to put a constraint, just a simple constraint on the availability of biomass. Thanks for the question.
Excellent. And just another question. In your view, what are the most cost-effective technologies to convert excess heat into a district heating network?
Well, that of course depends on the temperatures. So we have seen, not just in this study, but also in other studies that we did using the Embers tools, was that heat pumps are sometimes not cost effective in today's policies, and also not emission efficient in today's electricity grid, with the emission intensity of the grid. So I think high temperature sources are still with heat exchangers are still the most cost effective in today's energy prices and policies. But then with rising natural gas prices and so on, I think heat pumps and low temperature sources with a little bit more of support from uh, in terms of incentives would still be cost effective, especially if there are resource constraints such as biomass in the Swedish district heating system.
Thank you, Shravan. You have another question from Ido Abraham, and he says that we find that the district heating network infrastructure may be stranded if not coordinated with installation pathways for the building stock. What are your assumptions based on the demand side?
Yeah, so we have sort of not entirely captured this, but partially captured the insulation pathways for the building stocks in the the future demand projections for district heating system. So we've just considered the growth of demand to be mostly from new connections and not really uh, in the from existing connections, simply because the buildings are going to be better insulated. So we think the demand in the existing connections will not grow, and the only demand comes from the new connections to the district heating network.
All right. And well, in your view, a district heating network, well, you're only talking about fourth and fifth generation. What do you mean exactly? You want to lower the temperatures, but it would be better to lower the return temperature. Don't you agree?
Yeah, so that was exactly what we're thinking of uh, as well. But we're thinking of both lower supply and return temperatures on our in the model on the way to 2050. Uh, just because we could integrate these low temperature sources uh, in a more cost effective way.
Right. Thank you, Shravan. We now you have some more questions, but we go back to that late in the presentation. So now we have our final presenter, which is Antonio Faria. He is a researcher from Inesc Tech, um, working on the Embers platform as well. Um, just, and his presentation is titled Residential District Heating Network with Peer-to-Peer Market Structure, the case for Nordhaven District. Antonio, the panel is yours.
Thank you, Jose. Let me just share. Are you still sharing, Shravan? Sorry? Okay. Now I think it is okay.
No, we are seeing
So
your screen, Antonio. You can go. Yeah.
you can see?
Yes, we can see
Okay.
your screen.
Thank you. Okay. So, as Jose said, my name is Sérgio Faria, and I will be presenting the work entitled Residential District Heating Network with Peer-to-Peer Market Structure, the case of Northern District. I must say that this presentation might be similar to the one that my colleague Tiago did, since we are using the same platform and module. And I'll try my best to add different things to what he said, so you don't have to hear everything again. So this presentation will be sixfold. Firstly, I will briefly introduce the heating and cooling subject. Then I will discuss a bit the Embers platform and its modules, and in specific the market module. Afterwards, I will present the Nordam case study and the main results from the market module. Finally, the conclusions will also be addressed. Going to the introduction. Over the last years, technology's improvement have led to the distributed generation and alongside the arising of prosumers. Um, these prosumers are agents that can both consume or generate energy, and these players are responsible for the process of deregulation we are witnessing in the heat markets. There are a lot of industries like cement, supermarket, data centers, or end users as small buildings equipped with heat recovery units that can benefit from selling their heat to other agents that are in need of the same heat. This leads to a better market efficiency, especially in the heat market where the heat losses are of great importance. And with a deregulated market, um, all those that are involved are winners. Um, that's one of the goals of the Embers project tool, developed to match heat and cold and to let users assess different scenarios. Uh, these different scenarios can be useful to so these users are able to check the feasibility of new investments. Um, of course, this will also bring competitiveness to the field, and and this competitiveness is good because it will also it will also help to meet the European Union emissions goals. Uh, Regarding the Embers platform, um, it is composed of 5 modules, as Tiago already said. Um, the platform is still under development, uh, and we have the core functionalities, which aims to deliver sets of energy flows from sources, sinks, and links, as well as costs for excess heating and cooling recovery. Then we have the GIS, which identifies the possible network solutions according to some given characteristics and properties. This module connects all sources and sinks, and it gathers information about every pipe, providing data for each pair source sink, like the losses, the costs, the network length, and the installed pipe capacity. Then we have the TEO, and its purpose is to find the most cost-effective way, in the most cost-effective way, the combination of available technologies to use excess heat. In this module, a source evaluates the best technologies to meet the demand for one determined sink, while complying and respecting the constraints related to the regulation, it available, load profiles, techno-economic characteristics of technologies, and investment plans. Then we have the market module, which is the focus of this work, which allows users to simulate current and future trends for the heating and cooling markets, allowing them to choose the best market framework aligned with the user's economic, environment, and social interests. This may be especially important for users who have invested or are considered investing in waste heat recovery technologies. And finally, the business model is directed to different ownership structures, and it defines some parameters as net present value, levelized cost of heat, and internal rate of return. Um, Thus, the main goal is to set data exchanges between all modules, so they work as one. In addition, the modules are linked, as you can see in the figure, and there are a lot of data exchange between them, so the platform can run smoothly. Now, going a bit to the market, it essentially comprises three different market designs. The pool or centralized, where the agents communicate with a central identity, and all the energy trading is based on the decisions of this identity. Then we have the peer-to-peer or the decentralized, where agents are free to trade directly with other peers without the supervising identity. In this design, we also have the product differentiation feature, where bilateral trades can benefit from lower emissions or trading with closer peers. Finally, we have the community, where different agents are divided in communities with a goal to share resources, and afterwards, the communities can also share resources amongst each other. Um, in addition, the market is also divided in short and long term. So for the short term, it allows simulations up to 2 days, and it tends to give an overview of individual agents' performance when subject to different market features like block offers and energy budget. Uh, in this design, users are able to change some parameters and quickly check the effect of such changes on market results. In this way, the effects of different market settings can be studied in case studies with short time horizons. And on the other hand, we have the long-term market analysis, which can be used to assess market outcomes for agents in wider time range, like months or years. And it can go up to 20 years, a simulation. This is more suitable when users want to evaluate the profitability of potential investments. Also, there are other several results and key performance indicators users can check, like the energy traded between different agents, market clearing prices, operational costs, settlements, quality of experience, and so on. That is also a feature to indicate the best price one agent must bid in the market to achieve higher revenue. Now, going to the case study. Um, this case study is located in Nordam, in the city of Copenhagen, and it is composed of 30 residential consumers and a local supermarket. The residential buildings are supplied by the district heating grid operated by O4, and the district heating network in this area is already in place, and it is connected to the Greater Copenhagen district heating network. The local supermarket from the chain Many is capable of providing excess heat that could inject back into the Nordam district heating grid. The company Danfoss owns the heat recovery unit of the Many supermarket, but unfortunately, at this moment, this heat recovery unit cannot be connected to the district heating grid due to legislation obstacles in Denmark. This figure shows the resources in the area where the demonstrator is located, and the orange square it identifies the elements we are considering in this work. You can see the supermarket and the 30 residential consumers and the district heating network. Now, going to the results. I'm just showing some of it. For the short term, I'm showing the simple offer versus the block offer. This feature, we compare a simple offer with a block offer. So the simple offer includes the usual bid in the market. So an amount of energy is offered together with a monetary bid. And with the block offer, users are able to select periods where the offers can be fully accepted or fully rejected. This could be especially important to mitigate certain startup costs of some technologies. When looking at the grid results, there are no differences in the periods where the block bid is activated. You can see that the block bid is activated in periods 1, 2, 3, 4, and 5. But then we look at the periods 6 and 7 and we see some difference. This is related to the supermarket block offer. For the supermarket, we established this block offer 3, 4, 5, and 6. And we can see that this block offer is totally rejected in these periods. You can see it by the green graph. And we also see that in time steps 5 and 6, the grid is like a backup in the market, and the grid supplies the consumers while in the supermarket it is rejected. And then in periods 3 and 4 we can see that no energy is scheduled in the market because this will comply with the block offer and will bring better results to the market. Now going to the long-term results. Here I am presenting the successful participation in the market and the average dispatch generation. As expected, the centralized and decentralized present the same results, and the major differences are when using the product differentiation. Here one can see that both indicators lead to the benefits of the supermarket in the market. This is entirely linked to the fact that the supermarket is a low CO2 emitter and it is closer to the sinks. So obviously, if we are considering the distance and the CO2 emissions, the supermarket will benefit in the market. Regarding the social welfare, these values also decrease for the product differentiation, which is expected once we are penalizing some trades based on a preference, and this brings some monetary losses. Regarding the conclusions, this work allowed to prove the effectiveness of the platform and the links between the modules, especially the market module, since it returned valid results. The platform is also freely available for everyone to test it. In addition, it allows users to assess potential scenarios based on their own preferences, as we do with the product differentiation feature. All this together can contribute to a path of sustainable and a cleaner environment. And yeah, that's it.
Thank you,
Any
Antonio,
questions?
for the presentation. Does the panel have any questions? I have a question. So basically, what you're saying is that distributed networks distance is very important because the losses can be sometimes very burdensome on the final solution. So, in your view, what is the well? It depends, of course, on the case. It's a case by case basis. But what is the best approach, market approach for district heating networks?
It depends. I mean, in the long term, we have the option to. So if anyone wants to try it, we have the option for the user to select the CO2 emissions or the distance. And it really depends because the emissions are really important. We really need to minimize as much as possible. But then, if we consider the distance, will also be be we can decrease the losses, which also play an important role in the district heating. Uh, so it is up to the users and what exactly they see as the best option. And of course, that they can use this to simulate and to check the best outcome according to the preference.
Thank you, Antonio. Any other questions from the audience? All right. Thanks, everyone that attended this session today. I just want to give a quick note. So the Embers platform is a tool to quickly assess heating and cooling synergies. So assessing district heating networks for various groups of sinks and sources under different market structures, as you have seen here today, and under different ownership scenarios. I just added the link to of the platform, so if you want to test it. And thanks everyone for attending this session. And bye bye.
Thank you. Have a nice day.